In this module and this lecture, we go over examples of equations that use logarithms inside of the equations. And again, this is math for the analysis of electronic circuits. The last module introduced logarithms. This module covers the use of logs or logarithms in the analysis of AC circuits. Chapter 22 provides a number of example problems that have equations with logarithms as part of the equation. Key point: logarithmic equations can be solved either in logarithmic form or in exponential form. And let's take a look. Example 1, log n equals x. That same problem expressed in exponential form would be 10 to the x equals n. Or let's take a look at this. Natural log of a equals b, or in exponential form it'd be e to the power of b equals a. We'll start off with common logs. Let's take a look at the first example problem. The log of 73 equals t. We go through and solve that. Basically, you can solve it on your calculator. You hit log 73 equal, and what it comes up to is you put that here, and then you can rewrite it t equals 1.86. Of course, your calculator will give you the log of 73 to more decimal places, but this is sufficient for the lecture. Another example, log of y equals 4.73. That obviously is implying the easiest way to solve that is to quickly change the exponential form. You take the anti-log of both sides. In other words, the log of y as the exponent of the 10 will give you y, and 4.73 as the exponent of the 10 will give you this. And when you go and punch that in your calculator and express the answer to 3 significant digits, it'll come out to 5.37 times 10 to the 4th. The next example would be below. The log of a equals 7.83. Solve for a. Change it to exponential form. Of course, the log of a equals 7.83, and the 10 with the exponent of log of a will be a. So the problem becomes 10 raised to the 7.83 equals a. You carry that out, and a equals 6.76 times 10 to the 7th. And again, we only carry this out to 3 significant digits. Another example. X equals the log of 250. Take the log of 250. It's 2.4. X equals 2.4. A little more complicated example below. X times the log of 3 equals the log of 104. Excuse me. So, divide both sides by the log of 3. X times the log of 3 divided by the log of 3 yields x. Log of 104 divided by the log of 3. Take the log of 104, then take the log of 3. Carry out the division. You end up with 4.23. Next problem. X raised to the power of 3.6 equals 85. Find x. Well, the log of x to the 3.6 is 3.6 times the log of x. The log of 85 is as written. divide both sides of this equation by 3.6. So the log of x equals the log of 85 divided by 3.6. And that equals 0.536. So the log of x equals 0.536, and you want to find x. So the log of x as the exponent of the 10 will give you x, and this as the exponent of the 10 will give you this, and you carry out the calculation, you end up with x equals 3.44. Next example, 3 with an exponent of 1 minus x equals 12. Let's solve this. So we quickly change it into the log form. We take the log of both sides of the equation. So we're left with the log of 3 with an exponent of 1 minus x is equal to 1 minus x times the log of 3. Take the log of this side, that's log of 12. Divide both sides of this equation by the log of 3. You're left with 1 minus x equals the log of 12 divided by the log of 3. And you take the log of both of those numbers and you carry out the division, and you're left with 2.26 equals 1 minus x. Subtract 2.26 from both sides, and subtract x from both sides, and you're left with 1 minus 2.26 equals x, and x equals minus 1.26. Next example. 27 raised to the exponent of x divided by 3 equals 18. Find x. Take the log of both sides. The log of 27 with an exponent of x divided by 3 is x divided by 3 times the log of 27. That handles this side. For this side, take the log of it, log of 18. Divide both sides by the log of 27. You're left with x over 3 equals log of 18 divided by log of 27. When you evaluate those, this becomes 1.255 divided by 1.431, and that comes out to be 0.87. Now, multiply both sides of the equation. X divided by 3 equals 0.877 by 3, and you're left with x equals 3 times 0.877, or 2.63. Another example. Oh, I have that example on there twice. Okay, let's move on to one that hasn't been repeated. 4 equals the log of x divided by 100. Raise both sides of this equation to be the exponent of 10. In other words, find the anti-log of both sides. So this becomes 10 to the 4th on this side, and the log of any number as the exponent of the 10 gives you that. So log of x divided by 100 as the exponent of 10 gives you x divided by 100. So we're left with 10 to the 4th equals x divided by 100. Multiply both sides of the equation by 100, and we get 100 times 10 to the 4th equals x. And of course, this is equal to 10 to the 6th, or 1 times 10 to the 6th. Take a look at another example. 8 equals the log of 200 divided by x. Take the analog of both sides. In other words, both sides of the equation become the exponent of 10. So we have 10 to the 8th equals 200 divided by x. Multiply both sides of this equation by x, divide both sides of the equation by 10 to the 8th, and we're left with x equals 200 divided by 10 to the 8th, which equals 2 times 10 to the minus 6th. Next, we have a natural log, or the exponential form of a natural log. E to the y equals 83. Obvious question is, what is y? Well, we'll take the natural log of both sides. The natural log of e to the y is y times the natural log of e. Natural log of 83 is shown here. Now, make this the exponent of e, and you're left with y, and you got natural log of 83. Take the natural log of 83, and that gives you 4.42, so y equals 4.42. Let's take a look at another one. X equals 20 times 1 minus e to the minus 0.5. So we got 20 times 1 minus, and you go and plug this into your calculator, and it resolves out to be, to 3 decimal places, 0.606. Do the simple addition, and you got 20 times 0.393. Multiply that out, x equals 7.87. Another example, another natural log example. 5 equals 15 times the quantity 1 minus e to the minus 1 over x. Take the natural log. Now, let's not take the natural log yet. Let's divide both sides by 15. And we're left with just 3 decimal places, 0.333 equals 1 minus e to the minus 1 over x. Subtract 1 from both sides. You got minus 0.667 equals minus e to the minus 1 over x. Multiply both sides by minus 1. 0.667 equals e to the minus 1 over x. Take the natural log of both sides, and the natural log of e to the I had to straighten that out. Take the natural log of both sides. The natural log of e to the minus 1 over x becomes minus 1 over x times natural log of e. And the natural log of e is 1. So, and the natural log of 0.667, since it's less than e, will be a minus number. We come up with minus 0.405 equals minus 1 over x. Multiply both sides by minus x, and we're left with 0.45x equals 1. Divide both sides of the equation by 0.405, and we're left with x equals 2.47. You can go in the textbook and try the section review problems for chapter 22 and the end of chapter problems. And this concludes the lecture video for basic equations that have logarithms in them.